In the previous lecture, we have discussed about paging and we saw the basics of how paging works. So there we saw that with the help of paging, we are able to allocate non-contiguous memory locations to processes. So for example, we see that for this process P5, the first 4 pages, they are stored in these frames over here. And then the last 4 pages, they are stored in the last 4 frames of the physical memory over here. So we see that we are able to allocate non-contiguous memory to the processes. So now the problem we have is, how do we keep a track of which pages are present in which frames? Because we know that they can be present in any locations in the physical memory. So we need a track of which pages of a particular process are present in which frames in the physical memory. So for that, we are going to make use of this page table. Okay, so before we go into the details of page table, here are a few more things that we need to know. Every address generated by the CPU is divided into 2 parts, a page number and a page offset. So every address that is generated by the CPU, that is the address of each of the data that is present inside the pages of a particular process, they will consist of 2 things. One is a page number, which is denoted by P, and another one is a page offset that is denoted by D. So what is a page number? It is used as an index to a page table. It is the index of the page table, and then page offset, which is denoted by D, it is a displacement within the page. So we will come back to this in detail once we discuss about the page table. So the page table, it contains the base address of each page in physical memory. So the page table that we are going to discuss now, what does it contain? It contains the base address of each page. So base address is something like the starting address of each page. And then what happens? This base address is combined with the page offset to define the physical memory address that is sent to the memory unit. So we know that for processes, we are talking about the logical memory. The processes will have pages, and the base address of that page will be combined with the page offset, and that will give us the physical memory address in which that process will be stored. Okay, so this will become even clearer as we go further. So let us take an example and try to understand this. So for example, here we are going to see the paging model of logical and physical memory. So here we are having a process. So here I'm calling it logical memory. Think of this as a process, and this is divided into 4 pages, page 0, page 1, page 2, and page 3. And then here we have our physical memory, and this physical memory is divided into fixed size blocks, which are called frames. So we are having 8 frames here. So remember that the size of these pages and the size of these frames will be the same. Means the division that we make should be of the same size. So we have frames from 0 to 7. And now what we have here is the page table. So this is going to help us identify which page is stored in which frame. So for this page table, what we have here, these are the page numbers, and these numbers given here, these are the frame numbers. So what does this actually mean? Let's see, page 0. So it says that page 0 is stored in frame number 1. So if you look here in the physical memory, we see that page 0 is stored in frame 1. So similarly, page 1 is stored in frame number 4. So if you look here, page number 1 is stored in frame number 4. So similarly, page 2 is stored in frame 3. So page 2 is stored in frame 3, and page 3 is stored in frame 7. So page 3 is stored in page 7. So here we have a basic idea of how the paging model works for logical and physical memory with the help of a page table. So we see that this is a complete process, but this process is divided into blocks, and these particular blocks called pages are stored in non-contiguous frames inside the physical memory. We see that a part of the process is here, some are here, and there is another one here. So even though they are not contiguous, with the help of the page table, we are able to have a record of which pages are present in which frames. Alright, so that is the basics of paging model of a logical and physical memory. Now let's go into a little more detail, because here we have discussed about the process and the pages. Now within these pages, there will be data, right? Because this is a complete process, and when a process is divided into pages, each page will have its own data, and each of those data will be having some logical addresses. And using those logical addresses, they will be stored into these physical memory. And when it is stored in physical memory, it will be having some physical addresses. So let's see how we can translate that logical memory address to physical memory address. As we discuss about translation of logical address to physical address using page table, here we come back to the first thing that we discussed in the beginning of this lecture. So as I said, every address generated by CPU is divided into 2 parts, a page number denoted by P and a page offset denoted by D. So page number is used as the index to a page table. So it will serve as the index or the beginning of the page table. It will help us understand where is that page starting from. And page offset is a displacement within that page. That means within a page, what is the position of that particular address. So we see the first position, second position, third position, or whatever it is. So that is denoted by the page offset. So this will become clearer as we take this next example. So here, as we continue discussing about the translation of logical address to physical address using page table, I am taking a process over here. So this is the logical memory of the process. So let's say that this process is divided into 4 pages here, page 0, page 1, page 2, and page 3. And then here we have our physical memory, and the physical memory is also divided into fixed size blocks, and it is divided into 8 blocks here. So if you look here in this example, our page size is 4 bytes, because if you see inside a particular page, there are 4 bytes of data, 1, 2, 3, 4. So consider each one as 1 byte. So there are 4 bytes each in each page. So our page size is 4 bytes. And then what is the size of the physical memory that we are using here? We see that even in the physical memory, each frame will be of 4 bytes each, and we are having total of 8 frames. So what will be the total memory size of this physical memory? It will be 32 bytes, because frame size is 4 multiplied by the number of frames, which is 8, that is 32 bytes. So keep this in mind. All right, now here we have the page table. Now let's look a closer look at this logical memory. So here, keep in mind that this is a complete process, and process is divided into pages, and within the pages we are having this data which will be having some logical addresses. So this is the logical address of the data present in this page. So for page 0 we have data A, B, C, D. So for this A, the logical address is 0, for B it is 1, for C it is 2, and for D the logical address is 3. So similarly for page 1, page 2 and page 3, the data that is there and their corresponding logical addresses is given here. Now we need to see what will be the corresponding physical addresses for these logical addresses, and here we have our page table. So in page table it is mentioned which page is stored in which frame. So let's see here what it says. Page 0 is stored in frame number 5. So where is our page 0? This is page 0. What is the data in page 0? A, B, C, D. These are the data that is present in page 0, and it is stored in frame number 5. So where is frame 5? Here is frame 5. So we see that A, B, C, D is stored in frame number 5. So similarly, page 1 is stored in frame number 6. So in page 1, the data that we have is E, F, G, H. So that is stored in frame 6. So if you look at frame 6, we see E, F, G, H is there. And page 2 is stored in frame number 1. And what is the data in page 2? I, J, K, L. So if you look at frame 1, we see there is I, J, K, L. And similarly, page 3 is stored in frame number 2. For page 3, we have the data M and OP, and it is stored in frame number 2. So frame number 2 is here and M and OP is here. So we see that with the help of page table, we are able to identify where are the particular pages stored in this physical memory. Okay, now how do we translate the logical address to physical address? So for example, in this page 0, we have data that is A. Now this A is stored in logical address 0. So what is the corresponding physical address for this 0? We see that page 0 is stored in frame number 5. So if you come to frame number 5, we see that A is over here and A is stored in physical address 20. So we see that logical address is 0, physical address is 20. Now how do we arrive at this number? So for this, there is a formula that we can use to calculate. So let's see what is that. So here it says logical address 0 maps to physical address 20. And the formula for finding that out is frame into page size plus offset. Okay, so first of all, let us see what is the frame here. So for logical address 0 belongs to page 0. And what is the frame number for page 0? The frame number for page 0 is 5. So the frame is 5. And then we have to multiply it with the page size. So in the beginning itself, I told you the page size is 4 bytes because there are 4 bytes each in each of the pages. So it is 4. And plus the offset. So what is the offset here? So for logical address 0, that is this, the offset is 0. And why is it 0? Offset means it is the position within the page. So for 0, the offset is 0. Here, for 1, the offset is 1. And for 2, it is 2. And for 3, it is 3. Similarly, for page 1 also, this 4 is offset 0, 5 is offset 1, 6 is offset 2, and 7 is offset 3. So that is how we calculate the offset. So I told you that offset is the displacement within the page. That was the definition that we used, the displacement within the page. So that is the position of that particular address within the page. So we see that frame into page size plus offset is 5 into 4 plus 0, which is equal to 20. So we see that we are getting 20 here, and 20 is the exact physical address for our logical address 0. Okay, so this is how we calculate. So let's take another example. So let's say for logical address 3. So for logical address 3, it maps to physical address 23, it says. How can we find that out? Let's apply our formula again. For logical address 3, where is 3? This is the logical address 3. We have to find the frame. So we know that logical address 3 also, it is under page 0. And page 0 is in frame 5. So again, it is 5. And page size, it is always the same, which is 4 bytes plus the offset. Now, what is the offset here? Here, the offset of this logical address 3 is 3 because the position is 0, 1, 2, 3. It is in the third position. So the offset is 3. So 5 into 4, 20 plus 3, 23. So if you look here, this D or this logical address 3, it is mapping to the physical address 23. So we see this in the diagram. Also, we have proved it using our formula. So let's take another example again quickly. For logical address 4, it maps to physical address 24. So for logical address 4, which is this one, E, it is in page 1. It falls under page 1. And what is the frame in which page 1 is stored? We see that page 1 is stored in the 6th frame. So the frame is now 6. Page size is 4, which is 4 bytes. And the offset is 0 because here we see that this is 0, 1, 2, 3. It is in the 0th position. So it is 0. So 6 into 4, 24. And if you see here, E, it is in the 24th physical address in this physical memory. Okay, so let's take one more last example to wind up. Let's say we are now talking about logical address 13 and it says it maps to physical address 9. And let's find out if this is correct. So logical address 13 is over here, it is N. And this logical address 13 falls under page 3. And page 3 is in which frame? It is in the 2nd frame over here. So frame is 2 and page size is 4 bytes plus the offset. So what is the offset here? We see that this logical address 13, it is the first offset. This is 0, this is 1. So it is in the first location. So the offset is 1. So we have 2 into 4, which is 8 plus 1, which is 9. So if you look here, we see the logical address 13, which is this N, it is mapped or stored in physical address 9. So this is how we can find out or translate the logical address to physical address using a page table. So with this, I hope you have understood the function of a page table. And also I hope you understood the meaning of page number and page offset. And also we have seen how we are able to translate the logical address to physical address using this formula with the help of our page table. So I hope this lecture was clear to you. Thank you for watching and see you in the next one.